Buonasera a tutti, benvenuti. Scusiamo per qualche minuto di ritardo. Sono molto contento di vedervi così numerosi. Farò una breve introduzione in italiano, poi il seminario sarà in inglese. L'introduzione è sul progetto Vitality. Molti di voi sono parte di questo progetto, quindi conoscono già le cose che facciamo, però mi piace sempre ribadire che all'interno di questo progetto abbiamo avuto la fortuna, secondo me, e forse un po' anche la lungimiranza di prevedere un programma per invitare scienziati stranieri o italiani di altissimo livello che nell'arco di un anno passeranno, quando l'anno sarà finito, da 2 a 5 giorni presso la nostra università, presso gruppi di ricerca, stabilendo relazioni, allacciando rapporti o magari rinnovando rapporti esistenti. Questo è veramente un privilegio che dovremmo, secondo me, cercare di conservare anche per gli anni a venire. Non solo è la possibilità di ospitare persone di altissimo livello, ma in una fase come questa, in cui la ricerca scientifica a volte è messa in dubbio e portare avanti progetti di collaborazione può risultare difficile, questa è una piccola oasi che usiamo per attrarre ricercatori stranieri che potrebbero anche poi decidere effettivamente di spendere la loro carriera qui da noi. Oggi sono molto lieto di presentarvi uno scienziato di altissimo livello, il professor Kerry Emanuel, che viene all'MIT. Professore Emanuel ha già un rapporto con l'Università di Perugia, in particolare con il gruppo ricerca della professoressa Paolini, e chiedo alla professoressa Paolina Cerlini di presentare il professor Emanuel secondo le sue competenze. Prego.
Buonasera. Io sono veramente onorata di presentare il professor Kerry Emanuel, con cui ho una lunga relazione come molti degli scienziati che fanno questo mestiere in Europa e in America. Kerry Emanuel è stato l'advisor, il supervisor di molti PhD student, postdoc, che adesso insegnano in quasi tutte le università in America, in Europa, in giro per il mondo. Alla sua lezione conclusiva all'MIT c'era praticamente tutto il mondo che fa ricerca su questi argomenti, sia teorici che gente che poi applica queste cose, per esempio nelle agenzie federali americane. Kerry Emanuel ha lavorato per primo, tra i primi, sulla convezione, e oggi la convezione è uno degli argomenti più importanti riguardo al cambiamento climatico. La sua expertise è vastissima, ma in particolare i cicloni tropicali, la dinamica tropicale sono stati il focus di molti dei suoi lavori, e questo risulta essere adesso cruciale perché è proprio il bilancio energetico ai tropici che è un punto cruciale del cambiamento climatico. Oggi lui parlerà di molte cose, ma il suo lavoro spazia veramente su quasi tutti gli argomenti più importanti che sono stati trattati riguardo al cambiamento climatico. In Italia poche persone hanno lavorato con lui e sono sparse negli istituti, all'ISAC, nelle università, nel CNR, appunto ISAC, e adesso stiamo cercando di raccogliere tutte queste cose e connetterci ancora di più col lavoro di Kerry, che è ancora molto importante, ancora nel senso che continua a essere foriero di moltissimi risultati, come lo è stato nel passato. E quindi io dico solo che è fondamentale ascoltare persone come lui che hanno una comprensione profonda di cos'è il clima. Lui ha fatto modelli di tutti i tipi, semplici. La cosa più bella che io ho verificato, che forse vi posso dire qui, è che il suo insegnamento partiva dalla fisica di base per poi connettersi alle osservazioni e ai modelli del clima, dell'atmosfera, diciamo di quello che era l'insieme di tutti questi fenomeni, e riusciva a comprenderne alcuni aspetti fondamentali in maniera precisa e semplice da capire, anche per gli studenti che iniziano. Mi ha raccontato stamattina che ha fatto ultimamente un corso di climate change per gli studenti undergraduate. Lui lui insegna ai livelli più alti, quindi non faceva questo tipo di corso, ma ha pensato bene di farlo, e questo è una cosa molto importante anche qui. Quindi è molto importante, per esempio, utilizzare tutte le risorse che abbiamo anche sul web per cercare di capire il climate change. Kerry Emanuel oggi ci spiegherà alcune cose fondamentali del climate change.
So now, without much further delay, I'm very glad to introduce to you Professor Kerry Emanuel. At the end of the presentation, there will be time for a few questions, if any, and I'm sure that Professor Emanuel will be glad to answer and to talk to you. Thank you very much.
Thank you very much. Well, good evening. It's a very great pleasure to be with all of you in this very beautiful city. I'm also delighted to be in a country that allows me to talk about climate change. So it's one of the reasons I'm here. I want to, before I start to show you some slides and get into the science, I want to tell you something about climate science that I find, to my surprise, people may not know, is that it's very much like any other science that you've heard of, that the scientists who get into it because they're fascinated by nature, by this particular aspect of nature. What controls the Earth's climate? Why does it change? How has it changed over time, and why has it changed? If you are interested in science, I assure you this is a very interesting field. And it would be a very interesting field even if we didn't have to worry about climate change. So all of us feel a little bit awkward when we're put in the position of having to explain something that has a lot of social and political applications and implications. We're just not very comfortable with that. I hope to get you excited about the science for its own sake. Right? It's not just about what can science do tangibly for humanity, but think of science as a part of culture the way you think of art, of music, and so forth. It's part of our culture. Discovery is in our DNA. It's in our genes. That's why we're doing it. We're not doing it to advance some political cause, okay? Other people do that. Politicians do that. That's their job. My job is, as I see it, is to try to understand nature. Whatever message nature is trying to tell us about herself, this is what we're trying to understand, and it's what motivates us to go forward. Okay, so the program for tonight, I'm first going to tell you a little bit about a fascinating story, which is the long-term history going back 4 billion years of the Earth's climate. Okay, we know more and more about that thanks principally to the geologists, to the field of paleoclimate. And I'm only going to tell you a little bit about that story because I don't have time. But it's a really great story in and of itself. We'll talk about our own effect on climate. It's called anthropogenic effects on climate. How do we know we're starting to alter the climate? And then I will talk about what it actually means for us socially and as a civilization. What are the risks associated, and I should say benefits, because they're both whenever you change a system. Talk about the consequences of climate change. So let me start with the variations of the climate. And so this is an example of a record from the field of paleoclimate. It's actually a series of records. It's a time series. It starts 450,000 years ago and runs to the present, 0 meaning now, okay? And you see 3 curves on this. The top 2 curves are records from ice cores. And there's a lot of science behind them, but what you're seeing is an estimate of the Earth's mean surface temperature over time, okay? And the scale you see in degrees centigrade is over there. There are 2 ice cores, Epica and Vostok. And when you look at those temperature records, and you probably want to know, how do we know that? And it's a beautiful, fascinating piece of science. I have nothing to do with it myself, I don't do it, but it's really beautiful. It's all about chemistry, actually geochemistry, and it's not told very often. It's too bad. I wish there'd be a big documentary about why we know, how do we get these curves? Well, you see that there are these spikes, which we call interglacials. They're warm periods between ice ages. And we're in such a warm period now, you see at the end, all right? And in between, the temperature's 3, 4, 5 degrees colder, the global mean temperature, and the Earth was a very different shape, okay? Now, at the bottom curve, you see an estimate of the volume of land ice, not sea ice, but land ice, the volume of the great ice sheets, Greenland, Antarctica, and in the ice ages, much of North America and Europe. So you're probably asking, how do we possibly know that? It's another fascinating story. It also has to do with looking at the isotopic composition of water in ice, okay? I'm sorry, that's for the other curves. For this one, it's the isotopic composition of seashells buried in the mud at the bottom of oceans. So it's a wonderful detective story. But the ice volume is turned upside down, so low is up and high is down. So you can see by eye that when it's warm, we don't have much ice. And when it's cold, we have a lot of ice. That wouldn't surprise you. But this is very powerful evidence that the Earth's climate, going back 3 million years, you only see the last 250,000 here, had these fluctuations. And why? Well, we know the answer. I like to talk about what we know. I could spend the whole evening talking about what we don't know. In fact, I could spend the whole week talking about what we don't know. So I prefer to talk about what we know. But we do know that. Now, so for example, turn the clock back 20,000 years, which is not very long geologically, okay? Remember, civilization is roughly 7,000 years old, human civilization. Much of Northern Europe, all of Scandinavia, most of the UK were covered by ice, about 1 kilometer thick, all right? That's a lot of climate change. And that retreated over a period of about 8,000 years at the end of the last ice age. And as it did so, around the world, sea levels went up. So here's another time series based on an awful lot of work, looking at the geological record of sea level relative to today. So this is 24,000 years ago. This is the peak of the last ice age to the present. And this is sea level relative to today's. So 0 by definition today. But back here, 120 meters lower. Now think of what that would mean for our coastal cities. They wouldn't be coastal anymore, most of them, okay? That's a lot of sea level change. Now, if you look at this graph, about 7,000 to 8,000 years ago, sea level stopped rising and the climate stabilized into this interglacial. And by geological standards, the last 7,000 or 8,000 years have been remarkably stable climate. Okay? I don't think it's a coincidence that about 7,000 and 8,000 years ago that we, as a species, settled down, started to farm, started to herd animals, and so forth. We became civilized. The first signs of art, right? Paintings and caves date back to this period. This is when civilization started. And the remarkable thing about civilization over the last 7,000 years is how very carefully and finely it is tuned to the climate we've had for the last 7,000 years. So people sometimes ask, is this the optimal climate for us as a species? The answer is, by definition, yes. It's the climate we're adapted to, right? If you make the climate much warmer or much colder, there's going to be pain and suffering because we have to adapt way too quickly. Our ancestors adapted to this remarkably large sea level change without even knowing they were doing that because it took so many thousands of years to have happen. So, back to the question of why. Well, we've known why for about 100 years, and thanks to the work of quite a few people, but prominently the Serbian mathematician. Just a mathematician, not a geologist, not an atmospheric scientist. Milankovitch was his name. He lived from the end of the 19th century into the middle of the 20th century. And he knew and recognized from Newton's theory and from mathematics that in the Earth's orbit around the sun, there are some prominent oscillations. So if you focus on the top diagram, the Earth's orbit around the sun is not circular. It's elliptical. And the sun is at one focus. But the degree, how elliptical it is, varies on about 100,000 year time scale. It oscillates. Perfectly periodic or almost perfectly periodic oscillation. And that changes the distribution of sunlight over the planet with seasons. It doesn't change the net amount of sunlight intercepted by the Earth, but it changes how that's distributed among the seasons. Another oscillation has to do with the Earth's rotation on its own axis. And you know that the axis tilts with respect to the plane in which the Earth orbits the sun. But that degree of tilt, that's called the obliquity, oscillates. It oscillates for the period of about 40,000 years. So a bit faster than the ellipticity. And then, like a top, that axis precesses. And that also changes how sunlight is distributed with latitude. So Milankovitch said it's perhaps these oscillations in the Earth's orbit and in the Earth's rotation that are driving these ice age cycles. And we're pretty much now sure that he was right. It was very controversial when he came up with this idea, as many scientific ideas are. And most of the controversial ones are indeed wrong. But once in a while, one is right, and this one was right. Now here's evidence that Milankovitch was right. Well, this was a time series going back. So those numbers are thousands of years. So this time series goes back 1,000,000 years, or 1,000 years. And again, going to the right to the present. And there are two completely different quantities that are graphed on here. There is the amount of sunlight coming into the high latitudes of the northern hemisphere, the Arctic, based on Milankovitch's mathematics. That's the red curve, okay? Can you see the difference between red and black? Sometimes the colors don't come out. The black curve is based on the isotopic composition of seashells from the bottom of the ocean, going deep into the mud, all right? And it is, as I mentioned before, a measure of the volume of ice on the planet. And what this is telling us is that when sunlight is increasing, the volume of ice is going down. And when sunlight intercepting, again, the high latitudes, not the whole Earth, but just the high northern latitudes is going down, the ice volume is going up. You don't have to be a trained mathematician to see that these curves are fairly highly correlated with each other. But that was the prediction, okay? So we know why there are ice ages. There's a lot of things we would like to know better, like the exact nature of the response. This is a great accomplishment of science. I have nothing to do with it. I'm trying to boast to you because it's my colleagues in geology who did this mostly. But it's a great accomplishment to know now why there are ice ages. How many of you knew that? I'm sure some of you did, but it's not widely publicized. But that's on, I've been talking about timescales of hundreds of thousands of years. Let's talk about a longer timescale. This is a fossil, 65 million years old, from Alberta, Canada. And it shows a leaf of a palm tree. Right? Now, Alberta, Canada, 65 million years ago was not in a very different place from where it is today. It's very far up at high latitudes, but there were palm trees growing, and palm trees grow only in warm climates. So that's very different. Now here is an artist's depiction of what the climate looked like 100 million years ago in Antarctica. This is Antarctica, okay? We know based on fossil evidence that there was no ice whatsoever anywhere on the planet except maybe the highest mountains. It was like that. So why? Why could it have been warmer? The sun if anything, was a little bit dimmer back then. If you study solar physics, go back, just a little bit less sunlight coming in, but it was hot, even in places like Antarctica. And that seems to be, this is not for certain, but it seems to be because of changes in the greenhouse gas content of the atmosphere. So what we see at the top, and it's again based on geology, geochemistry, is a record of the Earth's surface temperature in degrees centigrade, going all the way back. Now there's uncertainty in these estimates. It's not perfect, this art of estimating temperature. And the coldest time on this time scale is where we are now. Or now in the last couple of million years, I mean. Okay? The bottom graph is a much more uncertain estimate of the amount of carbon dioxide in the atmosphere, with the current amount shown by this blue line. So the last 70 million years, I should have said this goes back 70 million years now, there seems to be a correlation between the amount of greenhouse gas in the atmosphere and the surface temperature of the Earth, as science predicted there would be. Okay, so let's talk about that science a little bit, the greenhouse effect. It's an unfortunate word because it has very little to do with the physics of how actual greenhouses work, but we're kind of stuck with that term. And really the science goes back to the mid-19th century, to the great Irish physicist John Tyndall. That's his portrait there. How would you like to have that man as a schoolmaster when you were a kid? You can imagine he was pretty tough, right? It looks pretty grim, but he was a genius, and he did many things in his career. And he built this apparatus, which you can now see in the British Museum. If you want to see it, it's still there. It's a long tube, and what he could do is he could fill that tube with a gas that he chose. And once he put that gas in that tube, he could shine light of various different wavelengths, blue, yellow, red, green, ultraviolet, infrared, shine it through and measure how much of that light came out the other end. So he's measuring how much light of a particular wavelength was absorbed by that particular gas. Because he wanted to know, by then it was understood that something in the atmosphere was trapping heat. They knew that, but they didn't know what it was. And he thought it must have been a gas of some kind. Now, if you were doing this, the first thing you would have done, the first thing I would have done, is tried the most abundant gas in the atmosphere, nitrogen. Nothing, no absorption of anything, any wavelength. Okay, let's try oxygen. Again, nothing. Is the apparatus working? What's going on here? I'm going to leave you hanging with that story for just a minute, okay, and talk about the physics of the greenhouse effect. And then we'll come back to see what John Tyndall actually discovered here. So what is going on here? Well, we can think of a very, very simple planet with an atmosphere just like ours, but with an atmosphere that has no greenhouse gases in it. And I've already said oxygen and nitrogen aren't greenhouse gases. They don't absorb any radiation at any wavelength. But we have a surface. And if we don't have any clouds, sun comes down and is absorbed by the surface. If that's all that was happening, the surface would get hotter and hotter and hotter. But the surface has a sink of heat. It emits infrared radiation, which you can't see unless you have infrared glasses, back to space. And the Earth gets just hot enough, the amount of infrared radiation goes up with the temperature. So as the surface warms up, there's more and more radiation going, until you get a balance between the sunlight coming in and the radiation. It's very simple to calculate that. I asked my undergraduates to do that in the first week. It's very simple. You get a surface temperature of minus 18 degrees centigrade. It's way colder than it actually is. It's actually closer to 15. And in fact, although they didn't do the math correctly, early scientists understood there had to be something in the atmosphere that was trapping heat. That something is greenhouse gases and clouds. So we'll defer clouds for a minute and just talk about greenhouse gases. There are greenhouse gases, and what they do is they absorb some of this infrared light. They don't absorb sunlight, generally speaking. They absorb only the infrared, but so that they don't keep getting warmer with time, they have to also emit it. But they emit it equally up and down. So if you're at the surface, you're getting radiation from two places, directly from the sun, just as much as you were before, but also from the greenhouse gases. Only you're getting that 24/7, 24 hours a day, 7 days a week, all the time. And so you have to get, the surface has to get warm enough to balance both the sunlight and the back radiation from the atmosphere. That's what's going on. And the greenhouse gases in our atmosphere make the difference between minus 18 degrees and 15 degrees. So let's get back to John Tyndall now. His results, and he was shocked by them, okay? The oxygen, as I've said before, the oxygen and nitrogen don't do anything. We also now know that argon, the next most plentiful gas in the atmosphere, also does nothing. And they all together make up about 99% of the mass of the atmosphere. So Tyndall was getting increasingly desperate and putting much rarer gases into his apparatus over time. What he discovered was that water vapor, carbon dioxide, and nitrous oxide absorb very strongly in the infrared. These are trace gases in the atmosphere. The difference for the scientists in the audience, oxygen and nitrogen are molecules made of two identical atoms. They're perfectly symmetric, and that has to do with their inability to absorb radiation. The other molecules are more complex, H2O, two hydrogen and one oxygen. They're asymmetric. They have all kinds of things they can do as molecules that the others can't do. It's a long discussion in quantum physics in the end of the day. But empirically, they didn't know anything about quantum. Tyndall didn't know anything about that. It hadn't been invented yet. But he discovered empirically that they did know that H2O was H2O. He discovered that these are the important greenhouse gases in the atmosphere. And even though they only comprise about 1%, they make all the difference between a climate that's habitable and one that isn't. So let's look at that in a pie chart. Nitrogen, 78%, oxygen, 21%, argon, 0.9%. Now, some of you probably can't see the orange sliver in there, which is the rest of it. Those are the greenhouse gases. If that little tiny sliver is why we're here. Without that sliver, we wouldn't be here. Okay? It sounds a little counterintuitive, but if I took not too many molecules of arsenic and put it on my tongue, I'd be dead pretty soon. Even though the mass of my body is, thousands of times that of a few molecules of arsenic. If there was an old-fashioned thermostat controlling the temperature in this room, it would be a little bead of mercury floating around in the thermostat that determined the temperature through feedback loops. So it sounds counterintuitive, but it's right. There's no argument among scientists at all about the correctness of this. But it's even worse than you think, because of those greenhouse gases, by far the most important is water vapor. But water vapor is a short-lived gas in the sense that the time it resides in the atmosphere is short. It's only about 2 weeks. It's constantly cycling down. And its concentration is controlled by temperature mostly. If I blew up a huge water balloon and doubled the concentration of water in the atmosphere, 2 weeks later it would be back to normal. So it's even a tiny fraction of that tiny fraction that's the carbon dioxide and the other long-lived greenhouse gases. Okay? And together they comprise 0.04%. That tiny, tiny, tiny amount of gas on long time scales controls the climate. And a lot of people didn't want to believe that when it was discovered 150 years ago, approximately, okay? But it's true. So we have to be now interested in what controls that 0.04%. Now, not very long after that, there's a Swedish chemist, Svante Arrhenius. He won a Nobel Prize in chemistry, and I forgot to put it on here. Here's a picture of him. Okay. I don't know about you, but he looks even more unhappy than Tyndall. Right? What is it about climate scientists that they makes them look so unhappy? I haven't figured. That's an exercise in social science. I haven't figured it out. But like a lot of 19th century scientists, he dabbled in things besides his profession. He was very interested in climate. And he did a lot of calculations based on exotic measurements, like how much infrared radiation is coming from the moon on nights of full moons. Many other things went into it. And then he made a prediction. The first one, that he started to worry, he was the first to worry that we were altering the composition of the atmosphere. And he calculated that if we succeeded in doubling carbon dioxide, the temperature of the surface would go up about 4 degrees centigrade. Now, this is before computers, obviously. He had very little equipment. It was a very early estimate. But it's pretty much within the range of what modern science thinks. Modern science thinks if you double CO2, you'll get a temperature change between about 2 and 5 degrees. And so Arrhenius' estimate of 4 degrees is pretty darn good, right? But he thought it would take thousands of years to happen because he couldn't predict how far the Industrial Revolution would go at the end of the 19th century. So we can ask, in essence, Arrhenius made a prediction that as carbon dioxide would go up, so would the temperature. Now we can test that prediction. And that's what you see on this graph. So this is going back to the year 1880. And the blue curve is the Earth's average annual temperature as measured by thermometers. There's a lot of science behind that I don't have time to go into. The red curve is the carbon dioxide content of the atmosphere. Or for the mathematicians or scientists, it's the logarithm of the carbon dioxide content, because the theory is that the amount of absorption goes as the log of the gas concentration. But they're very similar. And you could see it was a pretty good prediction. I'd say that was a pretty good prediction. The red curve is what Svante Arrhenius' calculations imply. He couldn't predict the carbon dioxide would go up. The blue curve is what actually happened. Now you can see there's a lot of noise. There are other things that influence temperature, most notably volcanic explosions, but a lot of material in the stratosphere that blocks sunlight. And then there's random fluctuations, which are weather on sort of the time scale of years. Pretty good prediction. 2023, when I made this graph, I have to update it every year because it's going up so fast, was the warmest year on record up to that point. All right. So that's one piece of evidence. Now we can go back in time further. Here is carbon dioxide going back to the year 1000. Now how do we know that? Ice cores. When snow falls on ice, it traps air bubbles. They become incorporated in the ice as little pockets of air. You can take an ice core and determine the gas concentrations in the bubbles. Very good, very accurate. We compare modern cores to records. That's what we did. 280 parts per million was the carbon dioxide concentration after the end of the last ice age. Very stable, and then starting at the dawn of the Industrial Revolution, up, okay? We did that. There isn't any doubt about that, not even among people who say that they're skeptical. And, well, today it's quite literally off the chart. In fact, I can see it on the screen, but you can't see it. It's 420 parts per million. This is a temperature record just of the Arctic, again based on proxies going back 2,000 years. You can see the slow decline of Arctic temperature following the Milankovitch curve until the 19th century. And then it started to be overwhelmed by the warming effect of carbon dioxide. We're pushing the system very hard and very fast. And you really can't do that and expect there to be no risks. Right? Just going back further in time, if we go back 800,000 years, we still have bubbles and ice cores. This is the CO2 level, okay? And it did fluctuate with temperature. And in that particular case, the causality was reversed. It was mostly the temperature change, not entirely, by the way, but mostly the temperature change that caused the carbon dioxide to change. We know that. But this, at the end, that spike, is the anthropogenic component. There are other trends. Here is a graph showing the trend, or the time change in sea level height, between 1993 and 2019 is measured very carefully and accurately by satellite. And the reason I'm showing you this is to disabuse you of a common misconception. Sea level change is not globally uniform. It's not like a bathtub where all the water goes up. And that's because of ocean currents, variability in the rate of warming, and very importantly, winds, which tend to pile up water in some places and not in other places. And so this graph didn't come through very well. Everywhere where it's red, you see sea level was going up, but it goes up faster in some places than in others. Most of the sea level change to date has been a response to the fact that water expands a little bit when it's heated. But it's beginning to be overtaken by the sea level change because ice sheets are melting and the water is coming into the sea. Okay, I think I'll skip that part. The other reason we know it's carbon dioxide is that here is a satellite measurement of the temperature trend at the surface. That's not uniform either. Global warming is not globally uniform. There are places that are cooling. I want to go back to the previous chart. You notice that south of Greenland, sea level is falling, and we know why. So some of you with a physics background might like to think about that, and you can ask me at the end of the talk. I'm not going to talk about it now. This, again from satellites, is the temperature trend in the upper stratosphere, way up high. It's negative. If the warming had been caused by sunlight, that would be positive. When you put more CO2 in the stratosphere, it cools it. And if you want to know why, I can tell you. It's very well understood and predicted that would happen. But it's a signature of the effect of greenhouse gases. And here's another thing that really doesn't have to do with climate, but just chemistry. The Earth's, this is not coming through very clearly, but the pH of the ocean in most places is falling. That is, the ocean is becoming more acidic as a direct effect of what happens to water when you dissolve carbon dioxide. And that's problematic because it's threatening biological organisms in the sea that build shells. We know from laboratory experiments that if you put too much dissolved CO2, they can't build shells anymore. So this is a real biological threat to the ocean. Now, when people talk about, especially when journalists talk about climate, they like to talk about climate models because you can show graphs like this. But I want to tell you that most of what we understand about climate does not come from models. It's very important for you to understand, not climate models anyway, okay? Science is not models. Models is a tool, are a tool. But here is, for what it's worth, an attempt by a set of climate models to simulate what happened to the Earth's climate roughly over the last 100 years. Okay, last 100 years. The black curve is the Earth's surface temperature relative to what it was 100 years ago. As it goes up, it actually goes down a little bit into the 1970s and 80s and then goes up again. The red curves are an attempt to simulate that with climate models where you put in the observed concentration of greenhouse gases and also volcanic aerosols. The blue is running those climate models again, but not putting in the change in the greenhouse gases. So the blue curves don't go up, the red curves do, and the red curves look more like what actually happened. It's another piece of evidence that, yeah, it's the carbon dioxide that's mostly behind the warming. By the way, sunlight has been measured accurately from satellites from about 1980. It's slightly going down, not very much, certainly not going up. All right, so now let's start to wrap up by talking about the future. The great physicist Niels Bohr, the Danish physicist, once remarked that prediction is very difficult, particularly when it concerns the future. So it's easy to do the hindcasts. The forecast of the past and future is more difficult. And scientists are acutely aware of our own ignorance, the problems we have to solve, to be more confident about predictions. We can confidently predict the temperature will go up, but by how much? That is where we're not so confident. And what are the sources of uncertainty? Well, first of all, clouds. Clouds do two things. They're the main source of reflection of sunlight, even more important than ice. So about 30% of the sunlight that intercepts the Earth is reflected back to space, mostly by clouds. That cool the planet. But clouds are also greenhouse agents. They also radiate infrared radiation down. And so they're working both sides of the street, okay, the clouds. And so what happens when you change clouds is complicated. Okay, cloud feedback, water vapor, we've already talked about. If you make the atmosphere warmer, it can hold more water. It's just plain old physics, thermodynamics. And generally speaking, the water vapor content itself does go up with temperature. That's a positive feedback, because water is a very important greenhouse gas. It makes the temperature go up about twice as fast, roughly speaking, as it would go up if water didn't change. The response of the ocean. It's very hard to observe the ocean below the surface and to model it. And then aerosols is another man-made effect where we put pollution in the atmosphere. We cool the climate with aerosols. And in fact, the dip of temperature I showed you before from like the 1950s to the 1980s, we think was due mostly to a huge increase in air pollution. And the subsequent rise was partly a result of the Clean Air Acts, which eliminated a lot of that kind of pollution. Clean Air Acts in North America and Europe mostly. Now, I happened to have just a week ago been in the Amazon River on a ship, and I took this photograph because it shows this. It's beautiful if you see the actual picture. It's not through the projector, but you don't have to have a lot of imagination to know that modeling how light and infrared radiation passes through a complex sea of clouds is enormously challenging. Climate models don't begin to resolve those clouds. Their computational nodes are 100 kilometers apart. These clouds are a few hundred meters, and they're thin, some of them. So it's a really, really difficult problem. That's the point of this picture. So when you put it all together, and you run a climate model thousands and thousands of times, this is a graph created by doing just that, where volunteers, could have been some people in this audience, said, yes, you can use my computer when I'm not using it over the internet. So we put lots and lots of computers to work, and we created this graph. We just changed parameters of the model within reasonable or plausible ranges. And this is the amount of temperature, of global surface temperature change we got in response to doubling carbon dioxide and then letting the whole system come to equilibrium. You can see there's a lot of uncertainty. And this is terrible from a practical point of view. The most probable outcome is 2 or 3 degrees, and that will involve big adjustments of society. There's about a 5% chance it will be less than 1.8 degrees, in which case we wouldn't have a lot to worry about. And there's a 5% chance that it will be more than 4.5 degrees, and that would be catastrophic. And this makes it a very difficult problem for civilization, because so much uncertainty in the science between the almost negligible and the catastrophic. It's not a terribly useful prediction, but it does give us some ground to estimate risk. This is just showing different generations of climate models, how much temperature change they predict as a response to doubling CO2. There's 1, 2, 3, 4, 5, 6, 7 generations. It hasn't changed all that much over time. And those error bars haven't really come down. So our ignorance remains, and we're acutely aware of that. Nobody tries to bury that uncertainty. It's there. And I won't talk about the right-hand panel of that too much, or this graph. The problem is, unless we do something, we're going to go much further than doubling CO2. These are projections of carbon dioxide content into the future, to the end of the century, that differ only in different modeling of our own behavior, basically. How much greenhouse gas we choose to burn, if you will. And it could go higher than a tripling by the end of the century. Okay, so the doubling is kind of conservative. We're well on our way to doubling now. And the problem is, as this graph shows, this shows what will happen in the future to carbon dioxide concentration on the top, all the way out to 3,000 years if, this is just a sort of a thought experiment, but it's actually an experiment you can do with a model, at some point in time, when the concentration reaches some level, we completely turn off the emissions. Obviously, we can't turn them off instantly, but we can do that in a model. The purpose of showing you this is to show you that at first the carbon dioxide decays pretty quickly. Well, pretty quickly is over 100 years. That's not so quick compared to our lifetime. But it takes thousands and thousands and thousands of years for the CO2 to go away naturally. So unless we can pull it out of the atmosphere, whenever we choose to stop burning fossil fuels, unless we can figure out how to take the carbon dioxide out of the atmosphere, we're stuck with whatever we have. The bottom graph is the temperature of the surface that goes along with those carbon dioxide concentrations. Notice those are even flatter. That's because of heat storage in the ocean. They're so flat that you can say basically when we shut off the valve, whatever temperature it is then is what we're going to be stuck with for 5,000 to 10,000 years. Okay, so that's part of the key part of the problem. Now I'm going to conclude by just very quickly going over what we think the important risks are. Increasing sea level. I've already talked about that. Increasing hydrological events. It's a very simple piece of physics, actually. It's beautiful. That if you warm the climate, the intensity of rainfall, that is how hard it's raining when it rains, goes up very quickly. But the intervals between rainfall also increase. So you have much longer periods without any rain at all. The average rain over the whole globe over a year goes up just a little bit, not enough to even worry about. But it gets concentrated into brief, heavy downpours, which are the things that cause floods. And that has a huge implications for food and water supply. You get, this is my own work, you get an increased incidence of high category hurricanes. We've seen that in the data. More heat stress and other health risks, all of which contribute, according to at least the US Defense Department, when we used to have one, to more possibility of armed conflict. There are benefits. Some increase in plant productivity, at least initially, because plants take in carbon dioxide. The limitations start to rapidly become apparent in other nutrients. And obviously a reduction in health problems that are related to cold weather. Okay? So we have to take into account the downside and the upside that people do, and taken as a whole, because we're so beautifully adapted to the current or to the climate of the last 7,000 years, it's a negative thing to change it. It's not a big surprise. Now, this is the last bit to show you something very important. A lot of the cost in human welfare comes from very improbable events becoming a little bit more probable. And just for the for the mathematicians, risk is formally defined as the integral of cost over probability. So the probability of something like an earthquake or a hurricane or a wildfire, the magnitude on this axis, that black curve is the probability. The really, really weak events aren't so probable. There's some maximum in the probability. And then the strong events are very improbable too. The red is the cost. How much will an event cost of a certain magnitude? That curve is invariably very nonlinear. It's not just a straight line goes up. You're basically multiplying those two curves. But because the cost goes up so rapidly, the main contribution comes from somewhere out in the right-hand tail. And we know where that is, again, from studying history. By the way, uncertainty increases the risk. It makes that black curve wider. And that increases that product. We know what that is, and I'll come back to what it is. But the main conclusion is that, point I want to get is nobody really cares that much about whether the temperature goes up a few degrees. You can get that by moving south or north. But we care about the risks that go along with it. Heat waves, wildfires, hurricanes, droughts, and floods. We need to quantify those risks, including the uncertainty, to make intelligent choices, and we're trying to do that. Insurance is one way of quantifying risk, but because insurance is now based on risks from historical records that don't reflect the climate change, they're not even accounting for the fact that climate's already changed. And this is killing the insurance industry in the United States. We can fix that by making risk estimates that are based on physics and not history. That's a whole other seminar. Science is now positioned to make very rapid progress in quantifying these individual risks. I think that's where we're headed in science. Finally, it's kind of obvious. We're very well adapted to frequent events. If the wind blows 30 miles per hour or 15 meters per second in Perugia, it's not going to cause much damage because it happens all the time, right? If it's very rare, 1 in 10,000 years, it's not frequent enough to worry about. Something in the middle is where you get most of the damage. And that middle, empirically, is around 100 years. And it doesn't matter if you're talking about a wildfire, a thunderstorm, or an earthquake. It's the 100-year events that contribute most to the long-term damage. This is just percent of property destroyed versus the return period of an event. Again, it could be an earthquake. It could be a hurricane. It's always steep around 100 years. So that's what we have to worry about. But historical records aren't long enough in whether they're not nearly long enough to define that 100-year event. Let me wrap it up. I've probably gone over time. So what I've tried to get across here is that several aspects of climate science are well established and have been for a long time. This is nothing particularly new. It's a really interesting field. I hope I got some of that across to you. Even if the climate weren't changing, it would be fascinating, and then we wouldn't have to worry about the politics. Earth's climate strongly bounded. It doesn't run away into an ice-covered Earth or do what happened to Venus with all the oceans evaporating, but it's pretty sensitive within those bounds, and again, we know that from geology. But physics supports that conclusion. Climate science goes well back into the 19th century. The Earth's greenhouse effect triples the amount of radiation absorbed from the surface. That's how strong it is. Sunlight plus 2 times sunlight from infrared radiation. But that back radiation is due to 0.04% of the mass of the atmosphere, the greenhouse gases. And the concentration of the most important one is increased actually closer, I have to keep changing the numbers, closer to 50% since the dawn of the Industrial Revolution. Beginning with the calculations of Arrhenius, we've known that doubling CO2 will change Earth's surface temperature around 3 or 4 degrees for every doubling of CO2. And that's consistent with modern climate models. The long atmospheric lifetime of CO2 limits the window of time that we can do anything about this. That's a bit frightening. We're altering the composition of the atmosphere at considerable risk to future generations. If you actually quantify these risks, including the uncertainty, they're pretty non-trivial risks. And we're beginning to see that play out in what's actually happening. And the climate change is felt mostly through extreme events like heat waves, hurricanes, floods, and wildfires. So I hope I've gotten across to you in a relatively short time some of the main things about climate science. But don't forget that it's also a fascinating endeavor of its own right. Thank you very much.
Okay, now we have time for a few questions, if any, from the auditorium. Please do not hesitate. This was extremely interesting in my opinion, so thank you very much. But let's hear a few questions.
I have a few questions.
Well, let's start with one.
Okay. I have been working on climatic change, not on the causes of it, but about the effect on the water resources.
Okay.
And I like a lot your presentation. And I have a few questions.
Okay.
The first one is, can you tell us something about why around Greenland the sea level is going down, as I understood?
Okay, so the question, I think, for the benefit of the recording is, why is the sea level going down around Greenland? It's a very kind of interesting and surprising answer. The Greenland ice sheet is very massive. It has a lot of weight to it. Right? You can imagine how many, many millions of tons of ice there are. But you probably know everything with mass exerts a gravitational attraction to everything else with mass. And among other things, the Greenland ice is attracting, if you will, water, seawater, up toward it. As the ice melts and runs off, that gravitational attraction diminishes, and the water relaxes back down faster than it's in that particular region where it's rising from other effects. So it's the decrease of the gravitational attraction of seawater to the Greenland ice sheet that's causing the ice to go down. In fact, it's one of the ways we know how much ice is melting in Greenland is because we can, by satellite, very accurately measure how fast the sea level is going down in that region. I hope that answers the question.
Yes, I have to think about it because it's not easy to see that in a quantitative way, but anyway,
Yeah.
thank you. The other question is, when you made the slide with the climate risks, you say that we should not worry about the 2-3 degrees of increase.
That's a bit of an exaggeration, but yes.
Because,
Yeah.
I think this is the point of view of people living in a continent where it is easy to move up and down because it's almost empty.
Yes.
But in other places, like in Europe,
Yeah.
it's not so easy to move north or south.
Yeah.
It's to move north.
Yeah.
So this is something that I do not agree much.
Yeah, and but even in that scenario, what you worry about, right, is if you are living in southern Italy and you're used to once in a while having a hot summer,
Yes.
and it's not nice, and sometimes people get ill because there's too much heat, that's where you feel it. And if those heat waves become either more frequent or even hotter, that's where you feel it.
Yes.
It's in the heat waves, right? So I'm not saying temperature isn't important. I'm just saying the shift in the mean isn't so important as the shift in the extremes. It's for almost everything having to do with climate, one could make a statement like that. It's the wings of the distribution where we're not well adapted, where we change. And that's the main thing. It's not that the mean doesn't count at all, but yeah.
And my last question maybe is just my curiosity. Did you show your presentation to your colleague Linsen, who does not believe that the CO2 is the maximum of the major effects on the temperature?
So actually, if you talk to Dick, he's actually a personal friend of mine. You might be fine. We don't agree, and sometimes people don't understand that when scientists don't agree, it's not personal. We argue with each other, then we go out and have a beer. That happens all the time. Dick is fully in agreement that the warming is being caused by carbon dioxide. Where he wasn't always in agreement on that, but he is now. And where he stands is that he doesn't think that it's going to cause very much problems for the human race. And he actually may be right in a funny way. So let me give you an analogy. You come to a busy intersection to take your daughter. Let's say you have a 10-year-old daughter and you're taking her to catch her bus.
Yes.
The bus, on the other hand, is on the other side of the road. It's about to leave. And if she doesn't run across the highway, she'll miss the bus. And you'll have to drive her to school and you'll be late for work. So there's a downside, all right? Now, supposing I'm a mathematician standing next to you and I know something about traffic, I say, well, if you let her run, there's a 90% chance that she'll make it. And there's a 10% chance she'll be run over. Nobody in this room would let her run, right? Of course. Because the consequence is, well, you have to take her to school. You do anything to avoid even a 10% risk. But the most probable outcome is she'll make it. So if you were a betting person and you didn't care about the girl, you were putting money on whether she'd make it, you let her run, you probably win the bet. Yeah. We're in that situation. It's a little bit distorted. That is, if we let it go, we might be okay. We might even be more than 50. I wouldn't say we're more than 50% okay. I mean, it's question is the cost of averting the risk more than the cost of the risk itself? And it may very well be true that it will be okay. We'll adapt and it will be fine. But we're taking a big gamble, not just with one child, but a whole generation of children. That's the way I look at it. It's a problem of risk. Okay? So I differ with my colleague on that. He's putting the money down. I'm worried about my kids. Yeah.
Another question? Well, while you think of the question, I have one myself. Mm-hmm. You mentioned models.
Yeah.
We physicists, we like models. We like to do models. I'm wondering, usually when you talk about weather prediction, we know we have very good models. We know most of the things that need to be known, but still we cannot make long-time prediction due to the strong nonlinearity in the models. Is this kind of trouble also affecting climate models or no?
To a much lesser degree. It's a really good question. So in case in case not everyone heard the question, we've gotten much better at computer modeling of weather. Almost all weather forecasts you hear beyond a few hours from now are based on such models, and they've gotten demonstrably better. Part of the reason they've gotten better is we can test them twice a day, figuratively, all the time, test them against observations. But we also know from the theory of chaos, which is one of the most profound theories of the 20th century, and it's not very well explained to many people, that prediction beyond some time scale is literally impossible, not just practically impossible. All right, so we're pretty sure we can never forecast the weather. We have all observations of every molecule.
Not longer than 1 week or so.
About 3 weeks. Well, maybe closer to 2 or 3 weeks, but it's somewhere in that range. But that doesn't stop us from saying that summer in Perugia will be warmer than winter in Perugia, all right? We can say that with great confidence. And we're talking about the statistics of weather. There'll be cold days in the summer that might even be colder than the warmest days in the winter. But in general, right, it's going to be warmer. So it's more like the second problem, where we have, instead of the annual forcing of the sun, okay, we have the fact that greenhouse gas is going up. So it affects the statistics of the weather. We can hope to predict that. And we can't predict the individual weather on any day. We know that, but we can predict certain, in some sense, climate is the statistics of weather, right? And we can hope to predict that. And we think we can, in principle. But there are too many practical limitations now that we're trying to overcome.
Any question?
I don't bite.
Yeah. Come on, don't be shy. Okay, Francesco, then David.
You showed the role of the CO2 as a greenhouse gas, and also the water vapor. No? But what about the methane production? Because methane is, I think it's increased in the last years.
It has. I'm glad you asked that question. I've been focused on CO2.
Please repeat the question.
Oh yes, let me repeat the question for the. So I talked about CO2 as a long-lived greenhouse gas, and I didn't really mention any other long-lived greenhouse gases. And the question was, what about methane? And I'm glad that you asked the question. Methane is very important. each molecule of methane is much more powerful greenhouse effect than a molecule of CO2, but there's a lot less of it. And it is contributing. So some of the graphs I showed you were what's called CO2 equivalent, if we convert methane into the power of the greenhouse of CO2. We don't worry about quite as much because its atmospheric lifetime is a lot less. That's a good thing. I mean, if we stopped doing it, the methane would go not very quickly, but much faster than CO2. But part of its decay is a conversion, a chemical conversion into carbon dioxide. So in the end, we're left with a little bit more carbon dioxide. But you're quite right, that's important. And they're the hydrofluorocarbons, which we banned in the Montreal Protocol, turn out to be really powerful greenhouse gases. And some of the warming has been because of those, but we're already thankfully controlling those.
David?
Thank you for your presentation. Just one question regarding a more, let's say, trivial aspect, in the sense that a lot of your work, I guess, revolves around weather studies and what we were talking about before when talking about risks. A lot revolves around mitigation aspects. Do you think, from your point of observation, that there is enough research and money spent into adaptation? Because from my point of view right now, I have to deal with management of a city, and so therefore my attention is more focused on what I can do today and the day after and so forth, not so much about the long game. So.
It's an excellent question, and I will repeat it. So the question is, are we putting enough effort into adapting to the climate? And my observation, it's not really my specialty, but my observation is kind of interesting, and I'll talk about the US just because I live there and I know about it. It's not because I think it's so important, but the federal government has been doing very little in the US to adapt, and this is true not just recently, but over a long time. And what's happened is very interesting from a sociological point. The other end of the spectrum, the smallest towns. I happen to live in a tiny town on the coast of Maine now. And they are doing a lot, small towns. And they're beginning, so you see these efforts, sometimes these are called grassroots efforts, but it's not so much individual people as small communities who feel they're being hurt by climate change. They're coming together, what are we going to do about this? We're going to build up a barrier, we're going to put in a seawall, we're going to try to plant a different kind of crop, different from different regions. And some of these communities are beginning to merge efforts. So starting at a small scale and merging up to a big scale, and maybe that's the way it should go. And what the federal government or this, whatever country you're in could do is to help the small towns and small cities in the first place, help them do that, rather than to try to manage it from above. I'm saying that empirically, not from a political scientist or ideological point of view. It seems to work best when it's happening first in small communities.
Yeah. Still on this line of thinking, it's interesting to see that what you showed us, it's a global effect. So it's affecting the whole planet.
Yeah.
But one could object that industrial production actually affected a very small fraction of the planet, at least very specific places.
Yeah.
So how does this affect what we do in a single location, affect the whole planet? Is there a diffusion process, something that takes time? How much time does it take?
So when we talk about the long-lived greenhouse gases, carbon dioxide and methane is long from this point of view, their residence time in the atmosphere is much longer than it takes a sample of air, say, to move between the poles. Mm-hmm. So from that point of view, it's well mixed. And if you measure carbon dioxide, if you stay away from big cities, which are big sources,
right.
If you measure carbon dioxide in Hawaii
Yeah.
or Antarctica, you'll get the same answer.
That's
and
interesting.
That does this. So the forcing, the radiated forcing, is from carbon dioxide is pretty much the same everywhere. but the response is hardly uniform. So the high latitudes of the northern hemisphere are warming, and were predicted to warm much faster for very interesting reasons than the low latitudes. But the low latitudes are getting more humid. From the point of view of human biological functioning, it's just as bad in the tropics as in the high latitudes.
Okay, thank you so much. Burul.
You show some very classical experiments made on the specific field setups to focus some specific features. Do you believe that some experiments can be done real scale in therefore to change, to understand if it is possible to change even if not the weather?
Okay, so the question was, from Bruno, was is there a possibility of countering, this is my understanding of the question, this warming, either globally or locally, by deliberately doing something to the system? And we have a word for that. It's called geoengineering. We're going to try to engineer the planet. The answer is that yes, absolutely we can do that. But there are risks entailed in that. So one thing that we can do starting today, if we wanted to, is to put sulfur in the stratosphere. And when sulfur goes in the stratosphere, it undergoes a chemical reaction, becomes a particle that you see as a haze, and it reflects sunlight. Nature has already done that experiment for us. It's called a volcano. Pinatubo put a lot of sulfur in the stratosphere, and the climate cooled for a few years and then came back because it was just one pulse. So we know that if we put sulfur in the stratosphere at a certain rate and keep doing it, we have to keep doing it because it comes out in about 2 years, it settles out, that we could cool the planet. No question we could do that. We even know quantitatively how much we have to do, pretty much. And it's extremely affordable. You know, one very wealthy person could afford to do this, a single person, very wealthy, right? It's not very expensive from a global point of view. So why aren't we doing that? There are a couple of problems from a point of view of the climate. The fact is that you're trying to counter a greenhouse effect, which is in the infrared, with a solar effect. And it's not a zero-sum game. In other words, you adjust let's say you want to adjust the temperature back to what it was in 1950. I'm just going to throw that number out to say 1950. You find that the rainfall will become somewhat less than it was in 1950. Okay? So you can't make the rain and the temperature back to what you want, both back to what you want it to be. You're going to have to compromise.
It's a complex system.
And then the problem is that then you start having legal and sociological problems. You know, there's a storm, and somebody blames it on the fact that you've been tampering with the atmosphere, and so they will sue you and so forth. There's a couple of other things I should mention is it does nothing to counter the acidification of the ocean, which I mentioned, the threat to marine biology, because you're still having a lot of carbon dioxide in the atmosphere. The other thing is that if you stop, if there's a war or something bad happens and you stop, you're really going to get in trouble fast. Because in 2 years, that sulfur will be gone. You have all this greenhouse gas, boom. You know, in 10 years, you're going to start to fry. So when you start to do it, you're committing yourself for thousands of years to do this. And so it's not a technical problem. It's not even much of a scientific problem. It's a political, legal, social problem. It's not my bailiwick, so I pass it on to you guys. But it is a decision for society, not for someone like me. Yeah.
Okay, we have time for one last question.
The question about the CO2, the sink of CO2 by weathering. What do you think can the weathering of carbonate or silicate rocks reduce or play a big role in reducing the atmospheric CO2, or it is not important?
So the question was, very good question, by the way, was can chemical...
I studied climate in the big past, so I have very interesting to this aspect.
Yeah, so the chemical weathering of rocks is in a geological system the main sink for CO2, and volcanoes are the main source. If we weren't here, that's what the balance would be approximately, right? There are other things going on, as you know. So we're now emitting CO2 at about 100 times the rate of volcanoes. So we would need about 100 times natural weathering. But there are things that can be done. By the way, what happens, you can explain it better than I can, but if you let rocks, certain kinds of rocks in particular, interact with water, some of the carbon ends up in the water and ultimately ends up in the bottom of the ocean. It goes into deep sea trenches. It's a very fascinating story, which I've tremendously oversimplified. But you could accelerate that in some way. So it's actually being done, you may know, in Iceland, an experiment where they're pulling air out, they're pulling CO2 out of the air and letting it interact with basalt. And when that happens, it becomes limestone. The carbon gets locked up in rock. It's not going to go anywhere. It's going to be there. And the question is, can you do that? Can you scale that up economically? The answer right now is no. It's not economical. But it may be someday. So it is an active area of research. And that's the cleanest way to do geoengineering, by the way, because you're simply reversing the bad things we've already done, rather than trying to put a sophisticated Band-Aid on it. Yeah.
Okay, thank you so much. We can thank you again, our guest.
Thank you so much.
Grazie a tutti, vi diamo appuntamento tra un mese, avremo un altro ospite in cui faremo una public lecture come oggi, sarà il premio Nobel per la chimica, il professor Savage, che starà qui con noi una settimana, la prima settimana di maggio. Grazie, arrivederci.